Now that we have some basic definition of solids, liquids, and gases, let's start talking about what forces are actually holding those molecules together. Because we need to have some force holding them together. If there's not a force holding them together, they're just going to fly apart. By the way, that's going to be what defines a gas. There's no more forces able to hold those molecules together, so they just go willy-nilly wherever they want. So when we talk about intermolecular forces, there are going to be four categories that we talk about. All right? And I'm gonna define these out of order because it's gonna make more sense to explain them that way. But I'm gonna put them in order from strongest to weakest. This is general. This is generally speaking because depending on the context, some of these might beat one or the other out. But just comparing the forces themselves, number one's gonna be strongest, number four is gonna be weakest. So our strongest force here, this is gonna be ion forces. So we're going to say ionic forces. And this is going to be important, even though we generally consider ionic forces to be a molecular force, not an intermolecular force, but a force holding a molecule together. We also consider it to be an intermolecular force, which is going to be in between molecules. So that's another way you can think of this inter word. This is going to mean in between. And we'll get to why we're really going to think of ionic forces as either or, as either in between or inside of a molecule. And just for our example's sake, we're going to use something like NaCl. Sodium has a positive charge, chlorine has a negative charge. These have these actual charges. Sodium does not own the electron that it gave away to chlorine. This is an ionic bond. And so we can have a crystal lattice where we have Na to Cl to Na to Cl, so on and so forth, over and over again, this ionic lattice building up to form a whole crystalline structure. We consider this an intermolecular force in this case because this is what's going to define the overall shape of the substance. It's going to be, if you look at a large chunk of sodium chloride, it is a large crystal. It is a very square, flat shape. So what about our next intermolecular force? Like I said, I'm going to go out of order here for a minute. Our next one is going to be dipoles. Okay, we're going to have dipole forces. This is going to be number 3 on our strength chart. Okay, so dipole forces. So remember back to when we examined bonding. When we looked at bonding, we had things like let's say methanone. Methanone is going to look like this. And we had these differences in electronegativity between the oxygen and the carbon, where the oxygen would hog the electrons in these bonds, giving this oxygen a partial negative charge. Now notice, this is a partial negative charge, where in sodium chloride, the chlorine has a negative charge, period. It is a full-on negative charge. It's not partial. It is not sharing that electron with that sodium in any way, shape, or form. That chlorine owns that electron. It's it. It owns it. It belongs to the chlorine. Bought, paid for. The oxygen is still sharing the electron with the carbon. So it's not a full ownership, so it's only a partial negative charge. Our next intermolecular force is going to be a stronger type of dipole forces that only comes up in 3 very specific types of bonds. That's why I put these out of order. This is going to be hydrogen binding. And you'll see this sometimes written as hydrogen bonding, but we're trying to get away from that convention because this is not a type of bond. This is an intermolecular force. It is in between molecules, so it's not a chemical bond. It is a type of intermolecular force. So hydrogen binding, this is going to be dipole forces occurring on 3 very specific bonds. This is going to be the hydrogen to nitrogen bond, the hydrogen to oxygen bond, and the hydrogen to fluorine bond. Now, the reason these are going to be so exceptionally strong is because nitrogen, oxygen, and fluorine are all the most electronegative elements. These are our 3 most electronegative elements. And the hydrogen that's bonding to them only has 1 electron to give. So when hydrogen bonds to nitrogen, well then, that electron that it has is mostly going to be hanging out around the nitrogen. So these are the 2 electrons that these are sharing. And when that electron is closer to the nitrogen, then all that's left over here is just a little positive charge. It's just a proton. And so we effectively have an exposed proton on one side of this bond. That's what makes this such a strong dipole. So this is going to be extraordinarily strong. So hydrogen binding is going to be 10 times. So this is 10 times stronger than dipole forces. So going from dipole to hydrogen binding is going to be 10 times stronger. So that's why hydrogen binding gets to be number 2, but we talk about it after dipole forces because it is a type of dipole force. So then our fourth type of intermolecular force is going to be called London dispersion forces. London dispersion forces. This is really going to be the consolation prize of intermolecular bonding because absolutely everything can do it. So let's consider something, a molecule that has no electronegativity differences. How about looking at oxygen a lot? Let's use oxygen here again. In this bond, these electrons, these oxygen atoms are sharing their electrons evenly. And so neither of them own it, so there's no dipole. So when these oxygen atoms get near each other, these two molecules get near each other, normally there would be nothing holding them together. There's no separation of charges. There's nothing that would actually want these to come together. But what can happen is the electron clouds around these molecules can sometimes move around. And just by pure chance, maybe most of the electrons are hanging out on the top of this one. And so on the top of this, we would get a very small partial negative charge. And on the bottom of it, we would get a very small positive partial charge. Well, if that happened right next to these other oxygen molecules, well, they would induce the same type of thing. The electrons in this oxygen molecule would go, oh, hey, that's a little more positive. Let's go hang out more over there. And so they're going to hang out more on that side, which would induce a very slight negative charge here and a very slight positive charge here. So we can look at these London dispersion forces, and those are really going to be in every molecule, but it's really weak because these are induced dipoles. They are very slight differences. And the only time it's going to be big enough to actually get something solid or liquid is when we have a ton of electrons. So if we look at oxygen's boiling point, when it's actually going to be a liquid, is going to be something like negative 170 degrees Celsius. Don't quote me on that. That's not exactly right, but it's in the negative 100s. But there are molecules that would be liquid at room temperature. Consider something like an oil. An oil is going to be a bunch of carbon to hydrogen bonds just over and over again. We might have 20 of these in a row, each one bonded to a bunch of hydrogens. Now there's no dipoles here. These are pretty neutral bonds. But across this, we have a bunch of areas of electron clouds where this whole thing could have an induced dipole where everything on this side is going to be negative. The electrons could move there, and when they do, they're going to make a very slight negative charge. And if there's enough of them all in a row, that can be big enough to hold these molecules together. Okay, so these are our 4 types of intermolecular forces. We're going to want to memorize them and memorize the differences. So when we're looking at ionic forces, these should be pretty easy to identify because this is going to be a metal plus a nonmetal. This is going to be just like any other ion that we've looked at, metal plus a nonmetal. And then when we look at London dispersion forces, we are looking for these exact types of bonds. If these occur anywhere in a molecule, we are going to have some hydrogen binding. So we've got something like, we could say an example of the O to H bond could be in water where it's oxygen attached to each of these hydrogens. But we could also say it's like in methanol, where we're going to have something like this. Or not an O there. That should be an H. Methanol would look like this. So even though it's got other types of bonds, it still has that oxygen to hydrogen bond. So that would give it hydrogen binding. Okay, so that'd be some HBs. All right, and then when we're looking at dipole-dipole forces, forces between these two dipoles, that's where we're going to need to go back to our VSEPR diagrams and still be able to figure out, does this have an overall polarity? So in this one, In this one, we're actually looking for polarity. And then if a molecule doesn't have one of those three, all that it's left with is London dispersion forces. So this is, you're going to figure out London dispersion forces by factor of elimination. Okay, so review, metal plus a nonmetal, easy to figure out. We should be able to look at the periodic table and figure out, does this compound contain a metal and a nonmetal? If it does, it's ionic, period. We should be able to look at, does this molecule contain any of these types of bonds? If you're unsure, look it up. If it doesn't have one of those, now we need to figure out if it's got polarity. This is going to be the one that's tough to figure out, okay? Because that actually requires us to look at the VSEPR diagram and look at the overall polarity. And if it doesn't have that, boom, London dispersion forces.